Hi everyone, my name is Rachel Sosa.
Hi, I'm Oscar Elizondo.
And I'm Lawrence Harrington, and today we'll be explaining inverse trigonometric equations and how to solve them. Some references we use for this presentation are Khan Academy and the Calculus textbook.
Okay, so I've decided to discuss the function f of x equals sine of x. And basically I chose this one because whenever we're being taught trig functions, this is the first one we've been taught, and I feel like it's the most important one, or like at least one of the most important ones. So the way we're gonna graph this, we're gonna use the unit circle. So here we have the unit circle, and we're gonna use that to see what values of sine of x correspond to every angle. So, and using that, we're gonna make a table. So we're gonna have theta and then sine of theta using the unit circle. So we're gonna see whenever theta equals 0, sine of theta will be 0 as well. So, and whenever theta equals pi over 2, sine of theta will be 1. So whenever we have theta equals pi, we're gonna have sine of theta equals 0 again. And then when it's 3 pi over 2, sine of theta will be -1. And lastly, whenever theta is 2 pi, sine of theta will be 0. So we can use those values to plug that into our graph. And since those are our set of points, and we plug that into our graph at the bottom, and we can see like the general shape of a sine function, and we just can keep going from that. Okay, so something important is that trig functions can share the same output for different input values. So that means that whenever sine of pi over 6 will be 1/2. So we can do that. We can see that by looking at the unit circle. So, but we can also see that sine of 5 pi over 6 equals 1/2 as well. And another example would be that whenever we have sine of pi over 2, that equals 1. And if you add a whole period to that, you'll get 1 again because it's a periodic function. So whenever you add a whole period, which will be 2 pi in this case, you'll go back to the same place. So you'll have the same value for that. And for sine of x and cosine of x, the period will be 2 pi, but for tangent will be just pi. Okay, so here we have the question, are the basic trig functions sine of x, cosine of x, and tan of x one-to-one functions? So if we graph them and we can pass a horizontal line through them, and we will see that the line touches a graph of more than one point. So they do not have inverses. However, we do use inverse of trig functions, and that is because we restrict the range for those functions. And I think Oscar is going to be talking about that a little more.
For my first question, I have the function f of x equals sine x, and I have a very poorly drawn graph of what Rachel was showing us earlier for the graph of sine of x. Now, the reason that and it's asking, why do we need restrictions for the domain? The reason we need restrictions for the domain is because if we look at the top graph of the function as a bigger whole, we can see that there are multiple points meeting up in the same location. So we can use a horizontal line test, which is the blue lines that I've kind of drawn through the graph. And we can see that there are multiple points at the same y. So to add these restrictions on the bottom example or drawing, we have the restrictions negative pi over 2 and pi over 2. We can see that the line passes the horizontal line test, which makes this ultimately invertible, which we need if we're going to be able to inverse the function, or the trigonomic function in this case, because if it is not able to pass the horizontal line test, then there is no way to have an inverse of the function because it is not one-to-one. And for my next problem, It asks, why is it natural for the functions to be equal? And the functions are y equals f of x equals sine of x, basically y equals sine of x, and x equals g of y, with g equaling the inverse of sine, or arcsine. So for the first equation, which is y equals sine of x, all we have to do is flip the variables x and y, and we get x equals arcsine, or sine inverse of y, because we also inverse the sine. Over here on x equals g of y, since g is sine inverse, or inverse of sine, we flip the variables and we get x equals sine inverse of y. That would make them, or arcsine for both, or sine inverse. It's basically the same meaning. And that's how you do 3 and 4.
As a result, it says choose an inverse function and explain how it works with examples. So what an inverse function I chose is f of x equals sine of x. And y f to the negative inverse of sine is parentheses the square root of 2 over 2 and equal to pi over 4. So going back to what I just said, we have to first look at the unit circle and see where pi over 4 falls on our line in our triangles. So looking at over here, we can see pi over 4 is at the very bottom, and it makes a degree of 45 degrees. So now we're looking for the height, and if this is true, is pi over 2 is over 2 is equal to pi over 4. So with it being an isosceles triangle, we can see that 45 degrees is on this side, and 45 degrees on the top side, making this a 90-degree angle. So we know why one is the hypotenuse, and this is x, and this is x. So now we're looking for this x. So it's basically like saying x squared plus x squared is equal to 1 squared. Breaking that down, we can just say 2x squared is equal to 1, because 1 squared is 1. And then breaking that down even further, we can say x squared is equal to 1 over 2, because x is like 1. And so from there, we can just say x equals 1 over the square root of 2, and then we multiply that times the square root of 2 over 2. And that just gives us our same answer. So that proves that this is the height, and that is the arcsine, our inverse of sine. And that is inverse trigonometry function.
Thank you, guys. If y'all have any questions, feel free to ask after the presentation ends.
That